All right, so today we're going to talk about the dot product. And the dot product is useful in mathematics because, and in physics of course, because it's going to relate to angles between vectors, it's going to relate to magnitudes of vectors, it's going to relate to projections, it's going to relate to many things that are going to be useful both mathematically and physically. So let's first of all start looking at the case of the two-dimensional vectors. So let's say we have a vector, let's call it x, and it's going to be a vector with coordinates x1 and x2. And then we have the vector y, which is going to have coordinates y1 and y2. And we want to define the dot product of these two vectors. So what you're going to have is you're going to grab x1 and you're going to multiply it times y1. Then you're going to add x2 and multiply it times y2. So now, what is the nature of this dot product? Well, firstly, you start with two vectors. You're multiplying two vectors, and you're getting back a real number. I'm going to assume all these vectors are going to be real vectors. You can, of course, do this for complex numbers. However, you're going to have to throw a complex conjugate. That's not what we're doing today. For us, it's real numbers. Okay? So that would be your definition. So you're getting a product of two vectors, and it's not giving you a vector back. So it's not a binary operation. It's giving you a real number back. All right, so with that, what if you all of a sudden wanted to have x1, x2, x3, so three-dimensional, and then y1, y2, y3? Let me erase real quick. I'm going to add the third coordinate, and then want to see what happens. All right, so now that we add a third coordinate, guess what we're going to do? Well, same thing. Have the third coordinate of the first vector times the third coordinate of the second vector. And like that, we get the dot product for three-dimensional vectors. Let's say that now we're not going to be working with vectors in 3 dimensions, but 4, 5, 6. Well, you keep doing the same thing, so you just keep adding plus dot 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 all the way xn, yn. So this concept is actually pretty portable. You can do it for n dimensions, no problems. So what all can we say about this product? What properties do we have? So firstly, let's talk about what algebraic type of properties we're going to have. So properties of the dot product. Well, firstly, it is bilinear, what is called bilinear, meaning that if you have a constant, so I'm going to break it into two steps. So if you have a constant alpha, and you multiply it times a vector, say u, and then you do the dot of that resulting vector with v, what you will get is going to be the same thing as if you had alpha and you multiply it times u dot v. So now notice here, alpha times u is a vector, dot v is another, dot a vector gives you a real number. U dot v is a real number, multiply times alpha is another real number. Similarly, you can move alpha into the next coordinate, and you get the same result in either position. Now we have to be a little bit careful. If you are talking about complex vectors that are used in physics and in mathematics, then whenever you pull a constant out of the second, in mathematics the second one out would give you a complex conjugate. In physics is actually the first one is complex conjugate, but different story for a different time. All right, another thing that you can do is there's a distributivity kind of property that if you have v plus w vectors and you add them and you then do the dot with u, the same thing as if you do the dot with u and v and add the dot with u and w. That is kind of funny. So that is going to be that you can separate sums. So these two together give you a linearity, or bilinearity actually, because the dot product is also commutative, meaning that u dot v is going to be equal to v dot u. So it's going to be commutative. All right, so with these three properties, we get a whole property that's called bilinear. I keep talking about it, and it just tells you that if you have, say, alpha u plus beta v, and then you do the dot with w, is going to be the same thing as separating alpha u dot w plus beta u dot v dot w. Let me erase and rewrite that. V dot w. All right, so, and that you can do on the second variable as well. So those are the properties, the most important properties we're going to be talking about. Now, there is a very interesting geometric property for the dot product, and I think I can still fit it here. Let's see how it goes. So if you have the vector, maybe I got too optimistic with the space. Let me erase this, and I want to redraw over here. All right, so let me draw it here. It's probably better. So let's say you have the vector u and the vector v. And then when you add vectors, say you place the vector, place a vector here, w. Let's put it in this direction. Let's see what that vector w would be. So when you add vectors, say you start here, v, and then on the head of v is the tail of w, you get that v plus w. So you're adding here is going to give you the vector u. So the resulting vector of adding these two is going to be this vector here. So again, remember that the addition of vectors is you place the first vector, then on the head of that vector you place the tail of the other. When you connect them, the resulting vector starting on the tail of the first to the head of the second gives you the sum. But now, then w, by subtracting on both sides v, is going to be u minus v. So this right here is going to be u minus v. It's kind of on a bad location. Let's put it here, u minus v. All right, so now let's talk about the law of cosine. So I have an angle here, let's call it theta. So let's think about this just as a triangle. Forget about that they're vectors. The length of this triangle, I haven't defined it yet. So let's go ahead and talk about the length for 1 second. And that's perfect that I started here because I can move over here and talk about the length of the vector. So let's talk about the connection between the length and the dot product first. And then I return to the discussion about angles. I'll be right back. All right, so let's go back to and talk about the length of a vector in 2 dimensions. So let's say that you have a vector just here with coordinates x1, x2. Not going to call it y because the next step is going to be 3 dimensions. But we know that we call the magnitude of this vector. We have called it before, or we have used it before. And it is going to be the length of this, the hypotenuse of this triangle, that by the Pythagorean theorem is just going to be the square root of the sum of the squares of these two quantities. Now, if we notice that what that would be just the vector, the square root of the vector x1, x2 dot x1, x2. Ooh, am I running out of space almost? Ah, no, perfect. All right, so that right there tells me then that I just wrote x. I meant the magnitude of x. Sorry about that. And what that tells us is that the magnitude of x is going to just be squared. It's going to be x dot x. Okay, so what happens when we go to 3 dimensions? Is that still true? Well, let's take a look. So let's go to 3 dimensions. Let's grab our vector. I'm going to change colors just so we can visualize what's going on. So let's say it's somewhere here. So what I'm going to do is I'm going to project this vector down 90 degrees to the xy plane. And this is going to be 90 degrees, even though my drawing is not that perfect, but let's say that is 90 degrees. So now, what happens is that if you think about this little triangle, I'm going to change colors. I use orange, so I'll use this here. So this right here would be coming from here. I would have the distance here, let's call it x1. The distance here would be x2. So the length of this right here would just be the square root of x1 squared plus x2 squared. Right? And now this distance here would just be x3. So now using this triangle, and that's going to get a little confusing, I'm sorry, but using this triangle, then the magnitude of this vector would be the square root of the sum of the squares, but one magnitude is this one and the other one is this one. The square of x1 squared plus x2 squared is going to give me just x1 squared plus x2 squared. And now the magnitude of this one squared is going to be x3 squared. So you see, I get the same formula for 3 dimensions. So in general, we're always just going to say that the magnitude of a vector x is going to be the square root of x dot x. Whether we're in 2 dimensions, 3 dimensions, or n dimensions, whatever that may be. Oh, in the screen, the picture doesn't look nearly as bad as I thought. Ah, good. All right. The magic of the screen. Anyway, so let's go back to our discussion now. So this is the connection that I needed. How we're going to determine the magnitude of a vector in terms of the dot product. So now I want to talk about the angle between 2 vectors. So let's return to this case. So we have the vectors u and v, and theta is the angle that is formed between them. How can we connect that to the dot product? So let me show you how it works. So we were, before our little interim here, we were talking about this vector w, which was u minus v. We had agreed on that. All right, so now we're going to talk about the law of cosines. The law of cosines tells us that the magnitude or the size of this line, I'm not thinking about it as a vector, I'm just thinking about it as a line. So the magnitude or the size of this line, u minus v, squared, is going to be equal to the sum of these 2 magnitudes, so u squared plus v squared minus 2 times the cosine, well, the length of this times the length of this, which is u v cosine of the angle. So that is the law of cosines right there. Now, if we expand this one out, what we're going to end up doing, and how we're going to expand it, is going to be using this right here. So the u minus v squared is just going to be the dot product of u minus v dot u minus v. We're going to have to use the properties of the dot product to FOIL it out. It looks a lot like just foiling, straight up foiling. But what we're going to obtain, and I'm going to skip quite a few of the steps here, we're going to end up with the following. Oh, notation, I'm so sorry. This is the notation you normally use for what is called the inner product, which is the generalization of the dot product. So that's what it would look like in your courses ahead. But right now I'm going to do u dot v. Sorry about that. So we obtain this. And I'm going to have to put the cosine down here. But when you set everything equal to each other and you start solving, you notice that this cancels with this cancels with this, and the -2 you divide it on both sides, and you obtain the equation that tells you that u dot v, so the dot product of u and v, is going to be equal to the magnitude of u times the magnitude of v times the cosine of the angle. So if you divide both sides by this quantity, you'd obtain that the cosine of the angle between the 2 vectors is given by u dot v divided by the magnitude of u times the magnitude of v. And now, if you take an arc cosine on both sides, then you can obtain the angle itself. Now, that will give us a lot of information. So let's take a look at what else happens, or what information can we obtain from that equation right there. So I'm going to erase this, and I'll be right back. All right. So now, there's several things we can think about. So when is the cosine of the angle? Let's take a look at the 2 cases when the angle is 0. So if the angle between 2 vectors is 0, what does that mean? Well, 0 or 180, either one, 0 or pi. That means that the vector, say u, is here, and the angle between them is either 0. I'm going to draw pi just to not mix colors. But they are collinear. They're on the same line. And when that is the case, then cosine of the angle, in this case is pi, would be -1. And so that what happens is that u dot v will be, or negative, I'm going to put the -1, is going to be the same as the product of the magnitudes of the vectors. So and if you put them, if they're pointing in the same direction, then the dot product will give you straight up the product of the magnitudes of the vectors. Now, why is that? Why would that be interesting? Is because two vectors are collinear if and only if they're multiples of each other. Non-zero multiples, I suppose I should say. And then if you plug that in there, what you're going to obtain is that the dot product of u and v is actually going to be equal to c times v squared. And that c then becomes a quantity that will become interesting to us in a little bit when we talk about projections. So that is just a curiosity in that case. Now, if the angle is pi over 2, so if they're orthogonal, that is interesting because by plugging pi over 2 here, you get that the cosine of pi over 2 is 0. Therefore, the dot product is 0. And this, by the way, is true. The converse of that statement is true as well. So if the dot product is 0, the two vectors are orthogonal. So the angle between them is 90 degrees or pi over 2. So that is going to be quite useful for us, the concept of orthogonality. So two vectors are orthogonal, and we usually write it as u orthogonal to v, if and only if the dot product between them is 0. So that is a connection there of the dot product that allows us to characterize orthogonality of vectors. All right, so the last thing I want to talk about is a projection of a vector onto another. And I think that's going to lay down all the theory for the dot product that we will need for, this is true for calculus 3 and also for linear algebra. So let's go ahead and erase here, talk about projections, and then we'll wrap the video right there. All right, so we're going to look at the situation where you have a vector u and say a vector v. And you would like to find the coordinate of u with respect to the coordinate v, or with respect to v. So basically you're going to project orthogonally, so 90 degrees from u down to v. And we want to know what would this vector be. So how can I write that vector? So, well, let's think about this angle. And so the magnitude of this vector, which I'm going to call the projection onto v of u, so that vector right there, I don't know if it's clear what so the vector from here to here, so the one that is right below our vector u. When I call that the projection of u onto v, I want to find out what that is. Well, I know what the magnitude of it is because that's a right triangle. And that is easy to do because that is going to be equal to the magnitude of u times the cosine of the angle. Hypotenuse times the cosine is adjacent, right? That's just your SOHCAHTOA or whatever it's called. And the cosine of the angle I can solve from my previous calculation, and that it was just going to be u dot v over the length of u, length of v. And if we cancel the length of u there with length of u, we get that this is just u dot v over the length of v. That's starting to look a lot like what I wrote over here earlier whenever the vectors are collinear. However, I don't want the magnitude of it. I want the vector itself. So what I'm going to do is I'm going to multiply this vector, this projection, times the vector of length 1 that is going in the direction of v. That is called a unit vector in the direction of v. And that vector is going to be given by the following. So I'm going to have the u dot v. Sorry, I have to write what I have first, not the magnitude. I already did the magnitude. So the projection onto v of u is going to be, and I should write one more equation before I write the final result. Let me write one more thing. And that would be equal to the magnitude of the projection onto v of u times a unit vector in the direction of v of magnitude 1, so it doesn't change the magnitude. So something that is going in the direction of v without changing the magnitude. But that's going to be that vector. And all I have to do then is substitute this in, where I get my formula for the projection of u onto v. And that's going to be given by u dot v over the magnitude of v appears twice, so magnitude of v squared times the vector v. Now notice this right here is a scalar or a number, because u dot v is a real number, the magnitude square is a real number, and then you're just scaling the vector v, and that gives you the projection. All right, so in the next video, I'm going to do a lot of examples relating to this and showing how this can be used in physics and in mathematics. So this video, let's consider it the theoretical background. I'm going to wrap it up here. Thank you for watching, and I'll see you in the next one.